Good morning, everybody. This is Mr. Dooley, and I'm going to teach you guys today how to find a quadratic equation from the solutions. In my class, I call this quadratic jeopardy. And the reason why I call this quadratic jeopardy is because if you have ever seen the game show Jeopardy, the gist of it is that Alex Trebek reads the answers and then the contestants give the questions. So that's why I'm going to call this quadratic jeopardy, because what we're going to be doing is we're going to give you the answers to a quadratic and you're going to come up with what was the question. So that's why I call it quadratic jeopardy. So question A, find a quadratic with roots -3 and 5. Okay. So there are two ways that you can go about doing this problem. The first way is that you can imagine what the factored form of this quadratic looked like in order to get those roots. So, for example, if you have a root of -3, what was the factor that root came from? Well, using a little mental math, it would be x plus 3. And x plus 3 would be the factor that goes along with that root of -3. And then how about the other root being 5? Well, the other root being 5, doing a little mental math, you find that the factor would be x minus 5. Okay? It follows a pattern. And this would be the pattern. That you take x, you minus root number 1, so x minus -3 would be x plus 3, x minus root 2. And then what you do is you just FOIL that out, and you will get x squared minus 2x minus 15. There it is. That's the gist of this entire lesson, is I give you the roots, and then you come up with a quadratic equation. Now, question B says find two more quadratic equations with the same roots. And so that brings us to the fact that this answer right here, this answer is not unique, which means there are lots of parabolas that have the roots of -3 and 5. Remember, in this situation, what we're looking at is we're looking at a quadratic equation that passes through -3 and 5. So this is -3, and this would be 5. So I think you can imagine that there would be lots of other parabolas that could pass through -3 and 5. You could go upside down. You could do one that would be really, really, really wide. You could even do one that would be really, really narrow. And so there are lots of quadratics that would have the roots of -3 and 5. So an easy way of finding two more quadratics is to pick some sort of constant. The easiest thing to do would be to multiply it by 2. And so you could just come up with 2x squared minus 4x minus 30. And that will indeed have the same roots as the one right above it, y equals x squared minus 2x minus 15. Those will have the roots -3 and 5. And then maybe try -2. That's a 2. You could do anything you want. any constant you want, but that's the idea. But the idea behind question number B, letter B, excuse me, is that when you get these answers, when you're doing quadratic Jeopardy, your answers are not unique, meaning you can come up with multiple answers. All right? So now let's take it up a notch. Let's do a problem where the roots happen to be fractions. And that's what we have right here. Our roots are going to be negative 2/3 and negative 1/5. Now there's a word that is capped in this, capitalized in this question. It says, find a quadratic equation in integral factored form with the roots negative 2/3 and negative 1/5. Integral factored form, and this word integral gets double underlines because it is a capitalized. So if we use the pattern from the previous question, which is right here, x minus root 1, x minus root 2, we can write this very, very quickly. This answer can be done in a matter of seconds. It would just be, it would be x plus 2/3 times x plus 1/5, stick a y equals, and I would be done. But this word integral right here means that you need to use integers only. Integral is the adjective of the word integer. And if you remember what the integers were, the integers is this set of numbers. It's the whole numbers and their negatives. So these are my integers. And if you notice, 2/3, not an integer. 1/5, not an integer. So how can I change this so that it is in integer? These are now going to be integers. Let's get that to be a 3 here. Very easy. See these denominators right here? That 3, that 5. What you're going to do is you're going to multiply this factor right here by 3. And you're going to multiply this factor right here by 5. And that will take care of the integer situation. So this will give you 3x plus 2. And this will give you 5x plus 1. And that is your quadratic equation in factored form. This is called factored form with integer coefficients. Integral. Okay, so just remember that integral means integers. By the way, that word integral is also an SAT word. They do use that on the SAT, so it's good to know that the word integral means you're only able to use integers. Okay? Now, so we've gone from easy to medium, and now we get to the more challenging type of problem. So we have another possibility of types of roots. We have the possibility that you end up with complex roots. So it says here, if a quadratic equation with real coefficients has a negative discriminant, then it has blank roots, which are blanks of each other. All right, well, what the heck does this mean? Negative discriminant. Negative discriminant. What is a discriminant? You guys remember what the discriminant is? All right, here it is. The discriminant is the stuff under the square root of the quadratic formula. So this right here is your discriminant, b squared minus 4ac. So what this statement is saying is, what happens if that discriminant is negative? What are we supposed to do? Well, it would be the square root of a negative value. And if you recall, that's going to be an imaginary number. So this is going to be imaginary roots, and they are going to be what we call complex conjugates. Complex conjugates, the conjugates part comes from the plus minus here. So that, for example, if you were doing the quadratic formula and you ended up with 5 plus 2i, then we know that the other root would be 5 minus 2i. Whoops. 5 minus 2i. These are called conjugates. And in particular, these are called complex conjugates because they are complex numbers. As Mr. Scott showed you yesterday, complex numbers have a real part and an imaginary part. So the second video that I'm going to do is going to be doing problems number 3 and 4, which deal with these complex roots. So I'll see you in a bit.